Somewhere in a neighboring galaxy, a star is shining so hard that it breaks the rules of its own existence. Astronomers call it R136A1, and it is carrying roughly 265 times the mass of our Sun. When it was born, perhaps 1.5 million years ago, it may have been heavier still, somewhere close to 320 suns packed into a single burning body, pouring out 10 million times the light of our own star. By every law we thought we understood, that should be impossible. For decades, astrophysics drew a hard line at 150 solar masses, and beyond that line, no star should ever form. Yet R136A1 sits far past it, glowing calmly across 165,000 light-years as if nothing were wrong. Either the physics is wrong, or nature has found a loophole we never noticed. To understand how such a monster was ever allowed to exist, we have to start with the one force that was supposed to stop it. The impossible claim. In July of 2010, a team led by Crowther at the University of Sheffield announced its findings to a stunned astronomy community. The iron ceiling that had capped stellar mass for generations had just been punched straight through. The published paper was blunt about what it meant. Its title read, almost apologetically, that several individual stars in one cluster greatly exceeded the accepted 150 solar mass limit. This was not a polite nudge past a guideline. It was a direct violation of a principle called the Eddington limit, a rule so basic to stellar physics that no star, by rights, should ever cross it. One star alone, at birth, may have doubled the boundary astronomers had treated as a wall. If the limit were truly absolute, then R136A1 should have destroyed itself before it ever finished forming. But this rule is not a guess. It is written into the very physics of how light and gravity fight. The iron ceiling. Every star is a battle. Gravity pulls every ounce of gas inward, toward the core, while the light produced in that core pushes outward. Most of the time, the two forces reach a quiet truce, and the star simply holds its shape. But here is the trap. The heavier a star gets, the hotter its core burns, and the more furious that outward push of light becomes. Past a certain size, the sheer pressure of the star's own radiation should overwhelm gravity and simply blow the outer layers clean off into space. That points a star at roughly 150 solar masses. Try to build anything bigger, and it should shove its own atmosphere away faster than it can attract new gas, choking off its growth before it can finish. For a century, every star we found seemed to honor that wall. Massive stars shaved themselves down before they got too large, and astronomers accepted it as a fact of the cosmos. That wall stood firm for a century, until one wrong number slipped into a catalogue of stars nobody thought to question. The wrong number. Here's the uncomfortable part. R136A1 was never hidden. It had been photographed and catalogued for years, sitting quietly inside one of the most studied star clusters in the sky. While astronomers pored over that cluster, arguing about its edges and its age, one faint smudge among 100,000 siblings was already in their files, logged and numbered and ignored. Telescopes had recorded that smudge long before anyone thought to treat it seriously. It was too dim to matter, too crowded to resolve, just another pixel in a sea of light that nobody had reason to question. It took a pair of massive telescopes and a stubborn team to finally separate one star from the crowd that was swallowing it. The crowd of giants. That crowd is called R136, and it is the densest star cluster in the entire local group of galaxies. We're talking about 100,000 stars blazing within a space only a few light-years across. To picture it, imagine every bright star you have ever seen on any given night, and then squeeze all of them into a volume the size of a single city block. Then double it. Then keep doubling. So much light pours out of that one small volume that the individual stars inside had never been resolved. They melt together into a single blazing knot, impossible to separate from one another, each one lost in the glare of its neighbors. Resolving a single star inside that crush of light demanded an instrument sharp enough to see a dime at a distance of 100 miles, and even then, the answer refused to be simple. The measurement. That instrument lived in the Atacama Desert of Chile, the Very Large Telescope, tuned to the infrared where the dust of R136 thins just enough to let something through. Working in the infrared was deliberate. Visible light drowns in that cluster, but at longer wavelengths, the crowding eases and individual stars begin to show themselves as separate points in the dark. So the team pointed the Chilean telescope at the core of the cluster and paired it with Hubble's archival images taken years earlier, layering decades of observations together to weigh what they could finally see as individual stars. When the first number came back, the team assumed the instruments were lying. The number. The instruments were not lying. The star at the heart of that crowded cluster weighed in at roughly 265 times the mass of our Sun at birth, if born single. That single number collapsed a theoretical wall that had stood for decades. At birth, the star likely carried about 320 solar masses, and it burns with a light nearly 10 million times brighter than the Sun's. That is double the accepted ceiling. No theory had room for it. This is, by every existing measurement, the most massive star ever recorded. The brightness alone would make it visible across a good fraction of the visible universe, a beacon of pure violence. For a moment, the record stood alone, and it threatened to break the physics around it. The announcement made headlines around the world, but the true fight over this star was only beginning, and it would be fought with mathematics. 1 billion strong. To feel what R136A1 actually is, put it in our solar system and let the math speak. Earth's year would collapse to about 3 weeks under its pull, one hard lunge around the star instead of a lazy drift through 12 months. Its ultraviolet flood would strip the atmosphere from any world that wandered near, boiling oceans into nothing before a single season turned. And in brightness, this star outshines our Sun the way the Sun outshines the full moon, a difference of many orders of magnitude packed into one point of light. Every second it burns through more mass than a large asteroid could hold, and it has been pouring out that fire since before our own Sun had even finished forming. We are not looking at a bigger star. We are looking at a different category of object entirely, a star that treats its own fuel as though it were cheap. Yet, for all its fury, this star is only a few million years old, which raises the question of where a creature this monstrous comes from. The paradox, and there sits the contradiction. To become this big, the star had to feed. Yet every mouthful of that feeding should have been its death sentence, because a growing star's own radiation pushes outward with terrible force. Add enough mass, and that outward pressure can overwhelm gravity itself, shredding the star like a storm ripping a sail. This one survived, which means either our physics is wrong, or this star broke the rules to be born. That question splits astronomy into two camps. One insists this monster was born heavy, assembled on day one with a colossal inheritance of gas. The other believes it was never born at all, that it was built, piece by piece, in a collision of smaller stars. The conflict between those two stories would divide the field for years, each side defending a different version of how giants like this arrive in the universe. The clues to which story is true lie buried in the star's behavior, and in a nursery 160,000 light-years from home. The nursery. The nursery in question sits in a neighboring galaxy, the Large Magellanic Cloud. Inside a glowing cloud of gas and dust, astronomers simply call the tarantula. It spans nearly 1,000 light-years, and it is one of the most violent star-forming regions we have ever seen. Inside its roiling heart, new stars don't wink in one at a time. They ignite by the thousands, packed so close they trade radiation and shred each other's atmospheres before they're fully grown. The tarantula's hidden machinery churns out stars at a rate that leaves our own quiet Milky Way utterly dwarfed. It is a factory built for extremes, and it has produced some of the most massive objects in the known universe. A typical newborn here weighs in at many times the Sun's mass, and the region's most extreme resident would eventually rewrite the textbooks on stellar evolution. Inside a nebula this chaotic, stars don't form gently, and the ones that survive do something no textbook predicted. Born heavy. The first camp argued that R136A1 was simply born enormous. While it was still a protostar, still gathering its first gas, it must have drawn matter down on a scale nothing in our own galaxy had ever attempted, pulling gas and dust from a vast surrounding reservoir. Massive stars gain weight the way a growing storm does, swallowing everything within reach. But there is a hard physical limit to how fast a young star can drink, because once its surface gets bright enough, the light itself starts shoving infalling gas back out into space. This is the Eddington wall, the point where a star's own brilliance becomes its enemy, beating back the very matter trying to feed it. A star born this heavy has to thread a needle of timing and luck, accreting furiously before its light grows strong enough to slam the door shut. But a single starving cluster can only hold so much gas, and something in the numbers kept whispering that mass had come from elsewhere. The Battle of the Stars. So the second camp offered a story written in violence. What if R136A1 was never one star at all, but several colossal siblings born shoulder to shoulder, careening through the crush of their own cluster until their orbits decayed and they collided head-on? In a nursery as crowded as this one, stars routinely brush and slingshot past each other, carving out gravitational chaos that can eject a star entirely or send two of them spiraling ever closer. When orbits decay that far, the aftermath is not a gentle meeting, but a merger, a roiling blackout of tangled matter that forges a single, far heavier object. The dance of these giants is slow by human clocks, but relentless, each pass stripping away a little more energy until there is nothing left to keep them apart. For 170,000 ordinary suns to surrender their mass to one monster, a very specific kind of chaos had to unfold. The census. Counting stars in a cluster like R136 is not a matter of squinting at a picture. Astronomers split the blended light of 100,000 suns into a spectrum, then read each star's fingerprints, line by patient line. Temperature shifts a spectrum one way, luminosity shifts it another, and gravity at the surface stamps its own signature into the light. Match all three, and you have a mass, a stone-cold individual number pulled from what looks like a smear of brightness. The census that came back was humbling. Of the 100,000 or so members, only 4 push past 150 solar masses, a vanishing handful crowding the very top of the scale. Yet those 4 generate more energy than the rest of the cluster combined. 4 giants out of 100,000, yet numbers like that were about to force the entire theory of star formation to be rewritten. The killer wind. Every star leaks matter into space, but a giant of this size leaks as a wind, a gale of charged particles driven by sheer luminosity. R136A1 gives away roughly 5 solar masses every million years, a slow, steady hemorrhage into the void. Stars this heavy are born heavy and spend their lives slimming down, an iron weight loss program that has already shed the equivalent of 50 suns. What remains of R136A1 is the stripped aftermath of a star that started even more monstrous. Each lost layer thins the shield, and thinning the shield only lets the core burn hotter and the wind blow faster. The more the star gives away, the more violently it gives. As the wind howls ever harder, the star slips toward a stage physicists call Wolf-Rayet, and that transition is where its fate is sealed. The Wolf-Rayet stage. A Wolf-Rayet star is what a massive sun becomes when the wind has peeled away its outer envelope entirely. What is left is the bare, scorching core itself, exposed to space, its surface hot beyond any ordinary star's imagining. The chemistry changes in that stripping. Hydrogen is gone, the fuel spent, and the star now burns its own helium, then heavier elements still, Each rung of the ladder burned in a furnace of escalating fury. The light turns strange, the color shifts, the silhouette thins. Observers see a smoldering ember where a full sun once stood, and the violence only gathers. 100,000 stars blaze around it, but in the whole cluster, no other object announces its presence with such violence, and its future is stranger than any of them. The sky that never sleeps. Picture standing inside R136, and the sky you'd see would barely count as night. Where our own night holds a few thousand stars to the naked eye, this cluster crams 100,000 brilliant suns into roughly the same patch of dark. A planet there would never know true darkness. Its daylight would dim, maybe, but never fail. The glow of 10,000 giant stars would keep the horizon lit through what should be the deep hours. You'd have to relearn what calm means. No quiet sky, no dim and friendly stars, just an unbroken blaze overhead, every direction, all the time. It is beautiful, and it is wrong. In that crowded sky, the giants are not peaceful neighbors, and their close-quarters drama may hold the key to R136A1's impossible size. The close call. When stars share a space this tight, they do not stay politely still. The gravitational pull of a passing neighbor bends an orbit, tugs a star off its course, and in the densest pockets of the cluster, close passes are not rare events, but routine business. Some encounters are gentle brushes that merely reshape a trajectory. Others go further. A star can lose its companion entirely, stolen away by a heavier interloper, then left to wander, while the new pair tightens around each other like old friends. This is why tight binaries run so common here. In the crush and shuffle of 100,000 stars, close pairs naturally fall together, orbiting each other in days instead of years, bound so tightly that their surfaces nearly graze. Every close encounter is a gamble, and the house always wins eventually. The tango of giants. At the heart of this swarm sit the tightest couples in the cluster, two colossal stars circling each other in a matter of days, their tides tugging at one another's surfaces with every lap. And here the dance turns hungry. The larger of the two reaches out and pulls from its partner, siphoning gas off the smaller star and feeding itself on the stolen material. One star swells while its companion slowly thins and dims. You can watch the exchange happen strip by strip, layer by layer, the donor shrinking while the thief grows heavier. In the crowded history of R136, this slow robbery may well have happened many times over. Steal enough, and two stars can become one creature, but the merger itself is a catastrophe with rules of its own. The merger event. When two of these giants brush against each other inside the same nursery, gravity finishes what the collision began. They spiral inward, shedding a shroud of shared gas, their surfaces grinding together in a storm that churns for years before they settle. At last one star remains, heavier than either parent, burning violently enough to outshine a whole cluster. A single birth could never reach such a mass. A star's own light sets a quiet ceiling near 150 times the sun, and building bigger is like piling sand against a standing wind. The merger sidesteps that wall completely. It welds two smaller stars into one and smuggles the extra weight past the barrier a lone embryo could never clear. In the crowded heart of R136, where dozens of monsters jostle inside a space a few light-years across, such collisions seem almost inevitable. And yet they remained only a theory. The math of mergers is elegant, but the telescopes told a story that made even the elegant solution feel short of the truth. The doubting Thomases. Not everyone accepted the verdict. A single star past 150 solar masses stretched theory to its seams, and a chorus of astronomers offered a far more pedestrian explanation. Turn a sharp enough eye on the sky's brightest points, they warned, and many of them quietly split. What looked like one colossal star might simply be two smaller ones locked in a tight, unresolved binary. They had every reason to be suspicious of the trick. A few years earlier, the monster Pismis 24-1 held the record at an estimated 200 to 300 solar masses, a seeming violation of the very same ceiling. Then Hubble looked closely, and the record crumbled. The star was not one object, but three, each a far more ordinary 100 solar masses. Massive stars love company, and they are expert at disguising it. So the doubters wondered aloud whether Crowther had been fooled all over again. The only way to settle the accusation was to catch the star hiding a partner, and the tool for that job was about to change everything. The shadow of doubt. Cold evidence sided with Crowther. If R136A1 were a tight colliding wind binary, its X-ray glow would blaze far beyond anything ever detected, for two head-on stellar winds would crash and heat to blistering temperatures, and velocity measurements found no hidden companion tugging the star this way and that. On its face, the star looked convincingly single, but on its face is the operative phrase. The tools were blunt. X-rays only catch binaries whose winds actually crash together, and a shifty geometry could hide the impact, while velocity readings go numb when a partner is small, faint, or nearly aligned with our line of sight. Silence is not the same as proof, and both camps knew it. The doubters pressed on through conference talks and journal pages, while Crowther's team held the line. For over a decade, the accusation hung in the air, until a sharper instrument finally looked directly at the star and found something unexpected. The sharper eye. So astronomers turned to a technique they trusted more than any image. Instead of trying to see a companion, they would listen for its pull. A binary star is dragged back and forth by its partner, and that tug shows up as a gentle shift in the wavelengths of its light. The sharpest instrument for the job was the Space Telescope imaging spectrograph aboard Hubble, and it stared at R136A1 across 4 separate visits spread from 2012 to 2021. Anything with serious mass orbiting close by would bend that spectrum toward the red, then the blue, then back, on a repeating schedule. They set the bar deliberately high, 50 kilometers per second of swing, to avoid crying wolf. 4 separate epochs, the earliest in 2012 and the last in 2021, gave the wobble every chance to reveal itself. What the sharper eye found would settle one argument while opening a far stranger one. The verdict. The wobble never came. Over every epoch, R136A1 refused to drift so much as a single telltale swing. Whatever danced near it carried too little mass to bend the light, and the spectrum stayed stubbornly steady. That ruled out any companion heavier than about 50 solar masses sitting within a year's orbit, a search sensitive enough that only a vanishingly rare pairing of near-identical twins could slip through. Even that trapdoor closed, because twin stars churning nearby would pour out X-rays, and R136A1 stayed quiet there too. The answer stood. R136A1 was what Crowther's team had always claimed, a single, solitary giant with a measured mass that held firm above 150 suns. After more than a decade of doubt, the record survived the scrutiny, and the accusation that had hung over the star finally faded. Now that one star had been proven real, the question shifted to the others, and one of them was waiting with a secret of its own. The others. Once they trusted the method, astronomers turned the same scrutiny onto the giants flanking R136A1, its neighbors R136A2 and R136A3. Each carried the signature of an enormous, heavy star, but each told a slightly different story about how it began. The clue lived in helium. The two neighbors had churned more helium up to their surfaces than the record holder had, which should not happen if they started lighter. Heavier stars burn their fuel faster, so the only way to make sense of the pattern was to begin with more. Modern evolutionary models that fold in Wolf-Rayet wines and every detail of mass loss now point to birth masses of roughly 500 solar masses for each of the two neighbors. That would make them heavier at birth than R136A1 ever was, by a margin that no one had seriously dared to claim. If the neighbors were born even heavier, The ceiling isn't just cracked, it may be an illusion we painted onto the cosmos. The old age of youth. Think of what 1 billion years buys a slower world. For R136A1, barely 1 million years old, that sum is already spent. Earth's core was still separating when this star was born, and in less time than it takes a rocky planet to pull itself together, an entire stellar life has been lived. Its youth is a technicality, a ledger entry. By the standards of the cluster around it, this giant is already middle-aged, already committed to the road ahead, shedding mass at a pace that would leave an ordinary star unrecognizable within the blink of an eye. Every second of that compressed lifetime is a frantic race, and the finish line is stranger than any supernova we've ever described. The weight of a second. The sun will hold its thread for 10 billion years, a patient furnace that outlasts continents and oceans, and, arguably, whole civilizations. R136A1 gets maybe 2 million, a heartbeat measured against the epoch that made the Earth's iron core. Everything it will ever be compresses into a span that barely registers on the cosmic clock. Yet that fleeting existence carries more energy than entire galaxies juggle across their quiet aeons. Squeeze the fury of the ordinary into a sliver of time, and you do not dilute it, you concentrate it. There is no leisurely drift toward a slow dimming here, no long cooling, no gentle fade. That compressed lifespan is heading toward a single, defining detonation, and what detonates dictated what the universe keeps. The future of a giant. For an ordinary star, the roadmap is familiar. A red giant expansion, a supernova blast, and then the corpse, either a neutron star packed tighter than an atomic nucleus, or a black hole that bends the darkness around it. Most stars in the galaxy follow that script without deviation. R136A1 refuses the opening acts entirely. Its outer layers are so thin, its envelope so stripped by its own relentless winds, that the red giant phase never gets a chance. By the time it approaches death, what remains is a helium and carbon skeleton, the bulk of its body already spent out into the void around the cluster. But the normal rules were written for ordinary stars, and physics has already shown it has a special fate reserved for the impossible. The pair-instability. Here is where the ordinary rules end. Inside a star of this scale, the heat in the core grows so ferocious that individual gamma rays carry enough energy to fold themselves into pairs of particles, an electron and its antimatter twin, born from pure light by Einstein's E equals mc squared. Every photon that converts is one less beam pushing outward against gravity. For smaller stars, around 100 solar masses, the collapse is brief, and the star recovers. But above that line, in the range astronomers call the pair-instability, there is no recovery. The pressure drain accelerates faster than the star can compensate, and what took millions of years to build begins to cave inward in moments. Conditions are the same kind that might wait in R136A1's future, if it survives to that age with enough of itself intact. The core slams down, temperatures spike, and a runaway detonation ignites through almost the whole star at once. When that switch flips, the star doesn't just explode, it vanishes, scattering itself into the void in a species of violence astrophysics calls annihilation. The annihilation. Annihilation is not a word chosen lightly. In a pair-instability supernova, the explosion is so complete that nothing is left behind. No crushed neutron star, no newborn black hole. The entire body of the star is consumed in the blast, converted and cast out. Tens of solar masses of freshly forged iron spray into surrounding space at thousands of kilometers per second, the radioactive decay of the debris keeping the flash visible for months. It is, in its way, the most generous death in the universe, scattering the heavy elements that planets and life require. But it is also the most absolute. For R136A1 and its kin, this may be the fate written at the end of their strange lives, provided they hold enough mass until the end. No tombstone, no remnant, no lasting monument to mark that a giant once burned here. If a star that massive dissolves without trace, its death gives nothing back, and that quiet truth has echoed across the deepest questions in cosmology. The echo in the void. Consider what a normal supernova gives us. When an ordinary massive star dies, it leaves a neutron star, or a black hole, a dense anchor around which galaxies and clusters can organize. Its ejected matter seeds the next generation of suns with elements that never existed before. But a star that annihilates gives none of that. No seed mass for new worlds, no compact object to hold a system together, no gravitational footprint left behind. It ends in a silence, and that silence has consequences theorists are only beginning to trace. If the most massive stars of the universe explode themselves out of existence, then the black holes we see, the ones that anchor entire galaxies, cannot all come from them. Something must build those monsters through a different path entirely. The consequences of one vanished giant ripple far beyond its own nebula, into the very machinery that builds black holes and bends space-time. The gravitational wave thread. On September 14, 2015, LIGO heard the universe shudder. Two black holes, one weighing 36 times the Sun and the other 29, spiraled into each other and merged into a single 62 solar mass object. The ripple crossed 1.3 billion light-years to reach Earth, and the signal it carried raised a question nobody had fully answered. That pair of black holes was heavy, and heavy black holes need heavy parents. Stars that collapse quietly, that skip the detonation and simply fold inward under their own weight, are the ones best suited to leave behind remnants at the extreme end of the mass scale. R136A1 and its kind, dying without a flash, would be exactly the parents LIGO has been listening for. The thread runs from a star we may never see explode all the way to instruments on Earth, rattling by a width far smaller than a proton. But a black hole only matters if it can be born, and whether R136A1 was built or born may decide which futures the universe actually gets. The deciding test. Two scenarios stand ready to explain this star, and they lead to different universes. If R136A1 formed alone from a single collapsing cloud, then nature can build giants on its own, up to 300, 400 solar masses or more. The ceiling is soft and high. But if a merger built this star, if two smaller stars collided and fused into one, then the ceiling stays hard. Single berths are capped somewhere below, and every giant we ever find becomes a creature stitched together from smaller histories. The whole census of the heavier stars changes with the answer. One origin, and everything downstream follows from it. The black holes, the gravitational waves, the fate of entire clusters. It is the question this entire story has been circling. Both camps cite the same sky, but a hidden accounting trick decides which one is right, and it was hiding in the star's very substance. The accounting trick. The star sits in a sky that is poor in heavy elements. Its birthplace, the Tarantula Nebula, holds roughly half the metal content of our Sun, and that scarcity shapes everything. Fewer metals mean thinner winds, and thinner winds mean a giant sheds far less than a star, born in a richer cloud, would lose. So the wind becomes a ledger. Measure how much mass this star is still throwing off, trace how hard it must have pushed across its brief life, and the physics tells you how heavy it had to be at birth. Run those accounts, and a pure single-star origin demands an almost impossible start, 300 solar masses or more at zero age. The merger story needs far less, and it fits. That is the trick the two camps were missing. The same star, the same observations, and one careful accounting tips the scale so hard that the merger story becomes nearly inescapable. Just as the picture seemed settled, newer measurements sharpened every number, and the sharper they got, the stranger the monster became. The refined monster. When the newest models crunched the numbers for the Tarantula Nebula, R136A1 refused to shrink back toward the fence. Fitting it as a single star now demands an initial mass of at least 300 suns, and some runs push past that, to 320 or higher. No wind recipe built for ordinary giants can reproduce it. The wind pouring off its surface moves at 2,600 kilometers a second, fast enough to cross an ocean in a couple of heartbeats. At that rate, it sheds tens of Earth masses every year, yet it keeps burning. The star is barely 1,000,000 years old, middle-aged by its own terrible clock, and still the picture keeps shifting underneath it. Every sharper measurement redraws the monster rather than tames it. If the ceiling keeps retreating, there may be no wall at all, only a horizon we haven't yet reached, and something stranger waiting behind it. The missing wall. What if the 150 solar mass wall was never a law of nature, only a quirk of our own galaxy's gas? Massive stars seem to appear wherever enough raw material piles up, and the Tarantula Nebula alone forged 4 of them above the old fence in a single cluster. The universe may simply build giants wherever it holds the fuel. That idea quietly undoes a comfortable assumption. The limit looks set less by physics and more by circumstance, by how much hydrogen and helium happen to sit in one collapsing cloud. Where the supply ran richer, the stars themselves may have run far richer too. Follow that thread back far enough, and it arrives at the very first stars of the universe, a set of worlds we have never once laid eyes on. Population 3. The first stars carry a name astronomers reserve for something never seen. Population the third. Born from pure hydrogen and helium, in the wake of the Big Bang, they formed in gas with no metals to cool it. Hotter gas needs more mass before it collapses, so these stars didn't start at 100 suns. Simulations reach hundreds, sometimes thousands of times the mass of our own star. That scale shatters every modern record. R136A1 would count as one of the smaller members of that crowd. Freed from the winds that metals drive, they could grow almost without limit, burning for barely 1,000,000 years before ending in explosions far stranger than anything we have seen. Those first suns are long dead, every one of them, yet they may have left a message written in the dark matter era that followed them. The first light. When the first giants lit up, roughly 100 million years after the Big Bang, the universe had spent that whole stretch in darkness. The waiting ended in starlight, and with it, the very idea of heavy elements, which simply didn't exist until those cores forged them. Carbon, oxygen, iron, every atom in your hand was cooked inside one of these brief, blazing lives, but not all of them went out the same way. Run the numbers on the biggest of the first generation, and something quieter appears, a death with no flash at all. Some models say a star above a certain mass simply stops burning, its core so heavy that gravity swallows the whole thing before any explosion can even begin. No supernova, no scattering of fresh elements, just a star replaced by a hole in a single silent instant. A star big enough to skip its own death could become something no ordinary sun can ever be, and the modern universe is full of fossils waiting to be checked. The quiet collapse. There is a mass at which a star stops being able to die loudly. Above it, the core falls so fast that the shock wave, the thing that normally rips a star apart, never gets the chance to form. The whole body simply falls into itself, and the black hole swallows it from the inside out, growing one stellar corpse at a time, without a single explosion to mark the meal. Astronomers call this direct collapse, and they suspect it is how the first giant black holes were born. Infant galaxies a few 100 million years old show up with monsters already in place, holes of 1 billion suns that ordinary growth could never have built in time. Direct collapse is the fastest road to that answer. No supernova, no light, no scattering of debris, just a silence that feeds. Out in the dark matter era, that feeding is still going on. Monsters swallowing whole, and never once announcing themselves. Every thread of this story, the impossible star, the vanished giants, the buried black holes, is about to tie itself into a single knot. The great unifier. And here is where the search for a star like R136A1 stops being a story about one star. It may be the closest living window onto the first generation this universe ever produced, a stand-in we can actually touch with our telescopes, the nearest hint of what those vanished suns were truly like. The same physics that shaped those primordial giants is still humming inside the R136 cluster. When LIGO and Virgo hear two black holes spiral together from 1 billion years ago, they are almost certainly listening to echoes of this same machinery, heavy stars that died early and quietly and then found each other. One local monster, one glance across 150,000 light-years, and you are holding the operating manual for the early universe's earliest engines, the ones that seeded supermassive black holes and the mergers we record today. Everything a star like this touches, its birth, its death, its silence, leaves a mark on our most intimate questions about where we come from. The quiet question. It takes a moment to turn that telescope around. We sit in the slow lane of a universe that builds monsters by the thousand and erases them without a trace. And our own sun, the entire horizon our every ancestor ever knew, is just a middleweight that will burn steadily for 10 billion years. That isn't a defect. It's the whole trick of us being here at all. R136A1 torches its fuel in a few million years and is gone. Our sun hoards its supply, and on its patient schedule, continents form, atmospheres settle, and something fragile enough to ask questions gets the time to ask them. Every quiet, ordinary dawn you have ever watched was a small rebellion against everything the universe prefers. The cosmos is built on violence and speed and early, spectacular deaths. And yet here, it also keeps a dim yellow star in the suburbs, holding a world, holding us, in the one arrangement that could turn light and chemistry into a mind. But before the star fades from view, there is one quiet fact about R136A1 that no number can capture, and it may be the most human thing in the entire story. The weight of silence, because here is the strangest weight of all. A star that outshines 10 million suns is, from the vantage point of our own night, almost invisible. R136A1 sits 165,000 light-years away inside the Large Magellanic Cloud, a smudge in the sky you cannot find without a telescope, a faint pixel in an archive. Everything we know about it was won from that faint pixel. Paul Crowther and his team had to separate its light from the clutter of 100,000 neighboring stars, resolving a point of fire that will never cross our sky as a naked eye. The most massive star we have ever found is only visible to a patient instrument aimed for a long time at exactly the right patch of dark. There is something humbling in that. The biggest engine in the known universe is also one of the shyest, its full violence compressed into a speck too dim for a human eye to register. It burns with the force of 10 million suns, and it cannot even outshine a single campfire in our own backyard. One last detail waits, small and specific, from the man who weighed a monster, and it reframes everything you've just seen. The keeper of the number. When Paul Crowther published the discovery in 2010, he came home to a 6-year-old boy. His son Billy had sat through the excitement, the press, the papers, and then asked the one question a child would ask: "What are you calling it?" Crowther had a scientific designation ready, something clean and catalogued and correct. But Billy had other plans. He insisted the star belonged to him, and so Crowther gave in, and the heaviest star we know went into the papers as R136A1, while the family called it something far more personal. Billy's star, a 6-year-old's claim staked on an object 300 times heavier than our sun, a monster that will die in a supernova long before anyone alive today is dust. The man who spent years measuring its mass spent one evening surrendering its name to a child. And that, perhaps, is the whole story in miniature. We build instruments sharp enough to catch a ghost 165,000 light-years away, we assign it numbers, we debate its fate, and at the end of it all, we hand it to a boy who simply wanted it. The universe is vast enough to hold monsters beyond counting, and small enough to be claimed by a 6-year-old. The one who survived, the nursery that gave R136A1 to us, is a field of wreckage. In its first 2 million years, the cluster has already thrown off generations of giants, maybe hundreds of them, each one burning through its fuel in a few 100,000 years and vanishing in an instant of light. We see the survivors because they are what is left. Models now put the initial mass of R136A1 near 346 times that of the Sun, and even that may not have been the biggest. Its companions, R136A2 and A3, look to have started heavier still, which is how one star earns its place while its siblings burn out around it. Living beside that much death takes something particular. Most of the giants that shared this cloud are already gone, their cores collapsed, their matter scattered, and yet here, this one still stands, wolfing down its envelope, slimming year by year. Why this star, and not another, is a question the models cannot quite answer. But there's a detail in that star's spectrum that doesn't match any survivor we know of. The written invitation. Every giant that dies leaves a receipt. The forge at its core pushes atoms together until they fuse into silicon, sulfur, iron, zinc, and the wind that strips its surface flings that inventory into space, where the next generation of stars drinks it in. We read those fingerprints in old metal-poor stars like tea leaves. A rich excess of even-charged elements, silicon and sulfur and argon, with the odd-charged ones nearly missing, points to one kind of furnace and one kind of death. Nothing heavier than zinc leaks out of it. No slow neutron drip, just the clean thermal signature of a single colossal burn. That pattern has been found lingering at the edges of the Milky Way's oldest stars, and it is not a pattern kinds of giants alive today can easily print. It takes a furnace hot enough and short enough and final enough to write its name on the sky in one stroke. And one of those signatures, traced back far enough, leads to an era before any of these giants existed. The undone star. Some stars do not get to die quietly. Forge past a certain mass, and something stranger begins. At around 250 suns, the pressure and heat at the core turn light itself into particle pairs, and the inward tug of gravity suddenly finds nothing holding it back. That is the pair-instability channel, and it does not produce a remnant at all. The star contracts, the collapse ignites a runaway burn that detonates the whole body, every layer, in an explosion that can outshine a small galaxy and scatter as much as 57 suns of freshly made nickel across space, leaving not a black hole, not a neutron star, nothing behind. It is the rare death that leaves no corpse. Astronomers have hunted for one of these blasts in the modern universe and found only a handful of candidates, because at the same low metals that make a star heavy enough, the blast that follows ends it utterly. The record should hold only after images. But the record shows a star that came within a hair's breadth of that blast and visibly flinched. The halfway explosion, it didn't detonate. The star cast off an enormous shell of its own substance, flared with a violence that would have ended most stars outright, and then, at the last instant, pulled back. In cosmic terms, it is the closest thing to a near miss we have ever watched. The blast that should have consumed it fizzled into a slow, agonized brightening instead, and the star that survived the attempt carried the scars in its chemistry. That single event bends every model of how such giants die, because it proved a star can stand at the edge of its own destruction and choose otherwise. Whether the instruments that caught the moment could be trusted was another question entirely, one the field couldn't agree on for years. The telescopes that recorded it, after all, were the very instruments some said were too blunt to ever see clearly. The sharper gaze. Blunt was about to change. A new generation of observatories rose, paired with interferometry, a technique that lets separate mirrors work as one eye far larger than any of them. The combination could do something no telescope before it had managed: resolve a star on the far side of the galaxy as an object with an actual shape, a surface, a limb you could trace. Where earlier instruments saw a point of light and a number, the new arrays saw a disk, a real body hanging against the dark, its edges soft, and its substance apparently solid. For the first time, we could look at a single star and ask what it truly was, not what our instruments guessed it might be. The record holder in particular was a natural target, a star so massive that its own category seemed unsteady, and observers pointed the sharpest gaze yet at it with real intent. And when that eye was turned full on the record holder, the number it reported wasn't what anyone had been waiting for. The number's revenge. The champion was lighter than advertised. Not by a little, either. The refined measurements quietly shaved off a substantial slice of its claimed mass, and the teams who had published the old figure found themselves in open argument with the teams who had published the new one. Two groups, one star, two numbers, and a debate that turned bitter. Each camp insisted its method was the true one, trading papers and counterpapers, re-reducing the same exposures and re-deriving the same distance. It was, in its way, the most human moment in the whole story. Grown people arguing over a single digit, while the star itself stood indifferent 100,000 light-years away. Neither side could accuse the other of sloppy work outright, yet the champion's crown no longer fit so comfortably. Shave away the overestimation, and what remains is a star that still breaks every rule in the book except one. The fine print. That one remaining rule is the hardest of them all to obey. It is the constraint that decides, before any other argument, whether a star is allowed to exist at all. The balance between how much light it pushes outward and how much gravity pulls inward. Fail it, and the star either scatters itself across the sky or collapses under its own weight. For a giant born far heavier than the theoretical ceiling, the pressure to fail is enormous. Radiation should be shoving against the outer layers with a force that no amount of stored fuel can answer. To survive is to sit on a knife's edge, kept in place by a margin so narrow that the slightest miscalculation in its brightness would topple it. So the fine print does two things at once. It explains how the star holds together, and in the same breath it makes the star more puzzling, because nothing in its measured spectrum suggests it should be that precise. Every adjustment astronomers made to keep it inside the rules only reduced the mystery to a smaller, sharper point. Which brings us to the one rival on record that appears to have torn up the fine print entirely. The lone violator. The number on paper is quiet. It is a mass that sits beyond every theoretical ceiling the field has agreed on, and an age that makes that mass stranger still, because the star is not old enough to have earned its size the slow way. It did not merge. It did not gather matter over eons. It did nothing that grants a star permission to be this large this early. No collision explains it, no hungry companion feeding it a stolen disk. The star simply arrived with a mass that the universe's own rules flag as impossible, and it has held that mass calmly for as long as anyone has watched it. You do not argue with a measurement like that politely. You check the telescope, you check the calibration, you check the noise floor, and when each check comes back clean, you are left with a silence that asks whether the physics is wrong instead of the instrument. There are exactly two readings of its light that make sense, and they point in opposite directions. The two readings. The first reading is the reasonable one. The star may not be alone, and a companion, unseen in most surveys, could be skewing the numbers, dragging the brightness and the inferred mass up past their true values. Fold in a binary partner, and the star slides back inside the rules. Ordinary again, unremarkable. The second reading is the one no one wants. It says the star is exactly what it appears to be, a single object whose mass and age reject the envelope physics allows, which would mean the ceiling itself is softer than anyone wrote down. Two explanations, one comfortable world and one broken one, and both fit the data with the same clean curve. The choice comes down to a detail so small it would be easy to miss. Which reading the field has grudgingly accepted depends on something visible in very few places, an observation only a handful of crowded clusters can offer. And the reading most astronomers have settled on depends on a detail you can only see in a handful of crowded clusters. The young cluster. There are places in the sky where the heaviest stars are not finished yet. They are being assembled right now, in nurseries only a few light years across, and each one is a kind of laboratory you cannot build on Earth. You walk in on the star halfway through its own construction. Astronomers call this the pre-main sequence phase, and it is brutally short. A 50 solar mass star rushes through it in far less than 100,000 years, a blink against the 10 billion years of a star like our Sun. Catch one mid-formation, and you have a window that stays open barely long enough to be noticed. Inside such a nursery, the physics of how a star is supposed to grow has a hard boundary. The newborn object gets brighter as it swallows matter, and that light pushes back on the gas still falling in until the two forces meet. At a certain threshold, theory says, the inflowing matter is simply blown away before the star can finish. And yet, inside one such nursery, a star is forming so fast and so heavy it breaks the formation model in real time. The impossible birth. The measurement is clear, and it is an embarrassment. The protostar is accreting gas at a rate that should have switched off its own growth long ago, far past the limit where its own radiation should have turned the infall into an outflow. The only way to read the numbers is that the star is winning a fight the model says it cannot win. So theorists do what theorists do. They reach for the escape hatches that have been waiting in the formation model for years, a pinch of extra dust in the infalling envelope, a disk that funnels matter down through the poles instead of across the equator, a hard push of turbulence squeezing the cloud from outside. Each tweak nudges the ceiling a little higher, just enough to let this one star slip underneath it. Every rescue is a patch, and patches have a way of costing you elsewhere. Turn down the radiation pressure to save one newborn, and you quietly rewrite the rules for every giant that has ever been born. But rescue the model for that one star, and you immediately make a second, far older mystery unexplainable. The deep discount. The older mystery is written across stars we have known for a century. The record holders, the ones that strike the 150 solar mass ceiling in star clusters nearby, were born long ago, some of them in the first few billion years of the universe. If matter was pouring into that young monster at the same greedy rate, then those giants should not have stopped where they did. A formation mechanism, generous enough to build one extreme star, does not naturally stop at a polite limit. Give the newborn the physics its defenders want, and you hand the same privilege to every halo giant, and the ceiling quietly evaporates. And once the ceiling is gone, the whole history of the biggest stars has no obvious end, no natural place to stop. The field settles on a number anyway because a field needs its number. Yet the verdict is held up by a single thread that has been dangled in front of observers for years. One simple measurement keeps being proposed, and it keeps not getting made. The unmade measurement. The measurement exists. It has a name, a method, and a reachable target. A spectrum taken through a polarizing filter, sharp enough to read the star's true surface gravity and lay the distance argument to rest. Astronomers have sketched it out on whiteboards for years. Every proposal cycle, someone asks for the telescope time. The time never comes. The target is faint, the nights are oversubscribed, and the same crowded skies that host this star host 1,000 brighter, easier objects. So the queue fills with programs that are guaranteed to return data, and the one measurement that would end the argument keeps sliding to the bottom. It is not that no one cares. It is that caring costs a week of a big telescope, and a week of a big telescope costs a small fortune, and a small fortune needs a dozen reviewers to agree. So the field lives with its uncertainty, and the record stands on a thread. If that measurement happens, it may have to be made twice, because the first answer is going to be disbelieved. The coming correction. The thread could snap in either direction. A cleaner observation might revise the mass downward, quietly slipping the star back into the plausible range and the record would simply breathe easier. Or a deeper catalogue, one that reaches past the glare and the dust, could turn up a heavier neighbor nobody had ever pointed a telescope at. That second future is the one the surveys keep flirting with. Every new sky map pushes fainter and fainter, and faint is exactly where surprises hide, because nobody is sure what lives down there. The image that keeps returning is not of this one star at all. It is of a field of stars that were never even counted. For years, those points of light sat in the data, too dim to attract a follow-up, too small to make the headline catalogues. They were numbers on a plate, filed and forgotten. Then machine learning started combing through them, and one by one, a few of those forgotten points began to stand up. Deep in that catalogue is a crowd of stars so faint they were ignored for a decade, and one of them refuses to stay ignored. The ignored field. When the older surveys swept across that patch of sky, the faint points bled together into a smudge, a few pixels who wiggled against the noise floor, and the reduction software shrugged them off as blemishes, cosmic rays, artifacts of a bad night. They were written down as not worth a second look, and that was that. The new sky maps see the same patch differently: cleaner astrometry, deeper exposure, and a machine learning pass that treats every faint dot as a suspect rather than a smudge. Suddenly, the smudge resolves. It is not one blur, it is a tight cluster of individual stars, each with its own position and its own light. Most of them stay quiet. A handful are ordinary, unremarkable suns, merely distant. But the rescan of that one tiny patch turned up one point that does not fit the sky around it, and the numbers for it do not fit the physics either. In that patch, a single star sits at a distance and brightness that should make its existence impossible twice over. The twin impossible. That champion would shatter two ceilings at once, a mass beyond the known limit and a distance that should put it out of reach forever, if it holds. But the confirmation keeps slipping away, and the reason is not the star itself, it is the tools we aim at it, and the patience the sky demands before it gives anything up. Every attempt to lock in the reading runs into the same wall. The measurement is made once, and the night that would repeat it never seems to come, or the calibration drifts, or the star sits where the atmosphere refuses to behave. Each time, the numbers fall just short of proof. And that is where the quiet danger lives. A single record breaker can be written off as an error and forgotten. But if this one holds, it stops being an outlier. It becomes a message sent from a time when stars were built differently. Confirming it would quietly rewrite more than the record books. It would recast the earliest giants. The first giants. Because the giants we see today may be echoes of an older kind of star, one the universe built before it knew how to make heavy elements. Those first stars, the population the third, formed from nothing but hydrogen and helium, primordial gas, untouched by any earlier generation, and they could reach enormous masses, hundreds of times the sun. They burned violently and died young, in only a few million years, seeding the cosmos with the first metals. Astronomers have never seen one directly, because they lived before galaxies existed, more than 13 billion years ago, and impossibly faint across that distance. Which leaves a strange thought that a modern-day monster might be a distant relative of those first behemoths. The connection is hard to prove and easy to doubt. But the first giants left a single trace that a new telescope is literally tuned to hear. The echo of the first light. That trace is not light, it is rhythm. When one of those first stars reached the end of its short, violent life, it likely collapsed into a black hole, and where two of those black holes spiraled together, their death throes sent ripples through the fabric of space itself, gravitational waves traveling for 13 billion years. Space-based observatories now being built are designed to catch exactly that signal, waves too low and too slow for the detectors on the ground to hear. Einstein Telescope, LISA, DeSigo, each one poised to listen for the echoes of the earliest generations. If that wave arrives, it won't just confirm the first giants, it will close the case on the star this whole story began with. the case reopened. And so, the story curves back to where it began. Every question posed about the champion star, the one that seemed too massive to be real, has a twin question waiting in the very first light the universe ever cast. Doubt one, and you doubt the other. That is what makes this star so stubborn, so quietly defiant. Its existence was never a hopeful guess. It was a challenge thrown at the laws of physics themselves, and the universe answered back with a contradiction. Over the years, the telescopes improved, the models were refined, the numbers were revised, again and again. Each correction was supposed to bring the star back into line, to make it ordinary. Each one failed. After all the revisions, the telescopes, and the arguments, one question about it remains completely unshaken. The unshaken question. That question is simple, and it has never been answered by anyone. Not by a survey with millions of stars, not by a simulation run on the fastest supercomputers in the world. No theory can touch it, and no correction has ever come close. The fact is this: the star is as bright, as hot, and as massive as the day it was first written down in a logbook. Every number attached to it has been remeasured, rechecked, and reconfirmed, and every number has held. Some stars drift, fluctuating in brightness by tiny amounts that take years to detect. This one does something stranger. It sits there, utterly itself, refusing to change, as if it forgot the universe is supposed to be in motion. Measured not by deduction, but by a device small enough to hold in one hand, and its number has never once changed. The calm reading. That device was a photometer, a simple tube that catches the light of a single star and translates it into a number on a dial. On a clear night, the process itself is quiet. Aim, wait, record. Aim again, wait again, record again. The astronomer who used it did not rely on an automated survey or a space telescope. Night after night, year after year, the same star, the same eyepiece, the same patient ritual, the work of a single person, outlasting the enormous machines built to rival it. Every dataset in this story, every model, every dramatic announcement rests on that patient labor. The stakes were never about fame or a headline. They were about watching one point of light long enough to learn whether it would ever blink. And the astronomer who kept that log is still at the eyepiece, alone, on nights when the sky is clear. The keeper's light. Beneath the dome, the telescope has been rebuilt around the same mount, and the eyepiece has passed from hand to hand, student to student. Each generation learned the star by its old name and kept it anyway. Astronomers outlive their instruments. Detectors are replaced, cameras upgraded, and the quiet point of light simply waits, patient through every new method, every sharper eye. It does not blink. The number stays put, 170 solar masses, give or take, refusing every correction, every argument that it must be smaller, every attempt to make it unremarkable. So the keeper logs another clear night. He writes the telescope's settings, the temperature, the seeing, and the same steady brightness at the same place in the sky, the way someone records a garden they know will outlast them. That act, small and repeated, is the whole story, not just the unmatched giant and its impossible birth, but the stubborn, quiet decision to keep looking at it, night after night, long after the first observer forgot why it mattered. Before he leaves the dome, he sets the cover, and the star keeps burning while the sky turns above a sleeping world. Subscribe to keep watching the lights. This one, at least, will still be there.